what I'm not going to do is go over every like fill in the blank for pages 3 and 4 because that's silly. What I'm going to do instead is talk about this water analogy and how it relates to circuits to help you kind of think about what to put and fill in the blank for that fill in the blank. So circuits are really a lot like water falling down a hill, all right? So when you think of like current and water, right, that's really the flow of water, right? So if you think about a river, like a river, the current of the river is really just the flow of the water. Analogous to that, electric current is the flow of charge, right? Charge can flow, it can move. So we know that point charges can move, and current is really just a bunch of point charges, electrons, and electrons moving together as a kind of a flow. That's really what current is. That's really the central idea of current. So what is going to make the water flow? You gotta have some sort of height difference, right? If there's water at the top of the pond and the bottom of the pond right here, if you're gonna get a flow, gravity needs to be able to accelerate. Accelerated gravity needs to be able to cause it to flow, right? If they're at the same level, you don't get any flow, right? If this is my situation here where they're at the same height, you don't get any flow. There is a gravitational potential difference. That's what you need in order to get water to flow. Similarly, you need I kind of gave it away. You need an electric potential difference to get charge to flow. This is called voltage, right? A voltage difference. So imagine, let's say I have like some wire. It's copper, so it's very conductive, allows the charge to flow. And I have a little bit of a light bulb here, right? Well, why aren't, right? There's charges on the rod, right? It's still neutral, but there's still electrons, right? Why aren't the electrons flowing to light up this light bulb? Because there's no potential difference, right? All the charge is at the same level essentially. So if there's no movement of charge, if there's no potential difference, it's not going to light up. As soon as you hook up a battery, right, which has a certain voltage, and I'm trying to draw this it's not bad. If you have a battery, as soon as you hook that up, the charges now will be able, there's a potential difference. They're able to flow. You get current, and that current will cause this light bulb to light up. All right, so that is what's going to be analogous. Like a battery is kind of like the height difference, right? Now, like if we're using that analogy. So now let's talk about a water wheel. Let's say I have a water wheel, and I want that water wheel to spin, right? So if I want it to spin, that's going to take some kinetic energy. Well, what you're going to see, say I got a water wheel going, right? I don't really know how to draw those things. But we need it to spin, get some rotational kinetic energy here. This water wheel is going to resist the flow of the liquid, right? So what's happening is the water is going to make it spin. I'm thinking about the fill in the blanks just to help you guys think about what to put in there. One question the thing asks is, hey, like if this was our current situation, the water would flow down, get this thing to spin, but eventually there's going to be no more water up here. All the water's going to get down here. This thing's not going to spin. What do you got to do? Well, what you got to do is you got to pump the water at the bottom all the way up to the top, right? That's what you got to do. And that is basically, right, and the reason we're doing this is to keep the water flowing, and the way we keep water flowing is by maintaining that potential difference, right? If there's a potential difference where some of the water's at the top, some of the water's at the bottom, water will flow, right? This pump is maintaining that potential difference. That is exactly what a battery is doing, right? Because the battery has to sustain a potential difference. Now take a look right here. If I want to bring water from down here to up here, you got to do some work, right? You got to give it some potential energy, right? That's going to take some energy, and if you're a human being, you're not going to have all the energy in the world, and you're going to get tired of taking all the water down here, putting it up top. That's why batteries die, because batteries have to maintain a potential difference, and they only have so much energy to really do that, right? And there's a video by Ted. I'm not a chemist. Really, batteries have to do with chemistry and chemical energy. You can ask Mr. Gustin about that, or you can watch this video I found on TED Ed. I honestly forgot a lot of it because I don't understand it. But regardless, batteries try to maintain a potential difference, even if I got some of the facts wrong there. Cool. We almost gave away the top of the whole unit. This wheel is going to resist the motion. Now, I'm not big on fluid mechanics, but if you're watching this after you haven't taken AP Physics 1, the added fluids, the equation of continuity, the idea that water flows at a constant rate. I'm not 100% sure if it applies here, because I don't know if that's like a close thing, but if the equation of continuity is true, the flow rate is the same. This resistor is not slowing down the water, right? So the water has some kinetic energy here, same kinetic energy kind of out of it. Well, how did this thing get rotational kinetic energy? It's kind of the change in UG, right? That height difference kind of causes it to spin. I might have gotten some of the physics wrong there, but what I'm trying to say is that the resistor does not slow down the current. The same way a resistor in a circuit. What is a resistor? It can be a light bulb. It can be anything that uses some of the electric energy in your circuit to make things happen. A light bulb, right? To shine light or whatever. In this case, it's like using the current of the water to make it spin, right? That kind of rotational kinetic energy. So that's what a resistor is. It resists the flow, makes it harder to flow, but it'll still flow the same amount in an electrical current. It will, right? Current isn't used up. It's always the same amount of current flowing through the circuit, right? If I have a battery, I'm going to draw my terrible battery. But if I have a battery, right, and I'm going to hook up some wires, and I got a light bulb, right? The current flowing through this thing, it's not being used up, it's the energy, and it's like the voltage potential difference that's kind of being used up, right? Because if you give it a voltage, the charge has some kind of electrical potential energy, and that's what's going to use up. It's going to kind of use up the voltage, and we'll learn that, like, hey, if this is 12 volts, this resistor is going to kind of use up 12 volts. Or if you have two resistors of the same resistance, they're each going to use up 6 for the total add up to 12. Don't worry about that if that's flying through your head. I'm just showing you that, yeah, these are really analogous, right? So I think that's kind of everything. I'm looking at the packet right now. I think that's kind of all the big ideas. We're going to talk about, actually, yeah, let's talk about resistivity here real quick. You know, if you make, wires can have resistivity. It's just like how much do you resist. A perfect, like, superconductor has, like, no resistivity, right? The charge can just flow through. But for something like wire, copper, yeah, it's going to have some sort of resistivity. Like, for example, if my wire here, right, if the pipe is, like, super rusty and, like gross and has a bunch of these, like what do you call it? Like, it pretends it's the intersection of the wire and has all these kind of, like, grime and dirt on the walls. Like, it's going to be really hard for the water to flow through. It has a higher resistivity compared to something that's clean. Same idea with what kind of resistors, right? If you make your wire longer, the resistance is going to be bigger, right? Because it's kind of go through, the charge kind of has to flow through more distance. Or if you make if you make the pipe smaller, it's going to be harder for water to flow through. If you make the, like, cross-sectional area, right? If this was your wire and I made it smaller, right? Pretend this is my really cool wire. If I made that smaller, hey, it's going to be harder for charge to flow. It has more resistance, and the packet will show you that equation. Hopefully it'll make sense. Hopefully this whole video makes sense. If there's any AP Physics 2, like anyone who's good at physics, like Mr. Gus, if you're watching this, I got some facts wrong, please let me know. You can comment, like anyone, if I'm wrong, comment it, please. Thank you for watching, though. Appreciate it.